Welcome to the course on computer design of electrical machine. We will have a lecture 37 today on design of axial flux machine part 2. Well, to start with presentation, we will start axial field switch reluctance motor. In short, we will call SRM. We will introduce, then we will go to application, then classification, then operating principle, then design equations, and of course, finite element design with case study and exercise and numerical example with the references like. So coming to this axial flux reluctance motor introduction, thus you can have a typically from this diagram you can have an idea that how the typically stator look like of reluctance motor of axial field type and how the coils are put typically on the stator like. So here you can have a further look for the axial field reluctance motor. The flux travels mainly along axis direction between the stator and rotor pole, as you can see in the typically in the diagram. And well, for the flux mainly along axial field between the stator and rotor poles, and you can just see how the flux is moving. I mean, in the diagrams, you can just have a look of the flux directions. I mean, typically in air gap as well as in how it look like in radial field and how it look like in axial field machine. So compared to radial field reluctance motor, axial field junction has the advantage typically of higher torque and power density and an adjustable air gap, and can be designed in special shapes to maintain larger diameter to length ratio, which is especially suitable for some applications. And this axial field reluctance motor potential of high torque density is especially important when powertrain has limited packaging space, and electric motors for in-wheel propulsion in electrified vehicles usually require a short planar motor. So some special structure of axial flux motor could benefit the machines with short iron flux path, and minimizing the iron flux path helps reducing the core losses. And because of its simple structure, higher power density and unique disc shape, axial field reluctance motors are a strong candidate for various type of applications, and such as flywheel, wind generator, pump, fans, valve, centrifuge, machine tools, robots, and industrial equipment. And coming to the application of this axial flux reluctance motor, the axial field reluctance motor have a distinct advantage of simple construction, structure, and high reliability, because besides they also possess properties of traditional axial flux machines such as higher power density, larger diameter axial flux reluctance machine to length ratio, and adjustable air gap and reduced iron losses, making it suitable for some application. And some of the common application of axial flux reluctance motor is like electric vehicle and hybrid electric vehicle, wind turbine, robotics and automation, industrial machinery, aerospace and aerospace systems, and renewable energy system, and home appliances. And typically you can just see how for your typically axial flux reluctance motor looks like for electric vehicle. I mean, like you can just see as a kind of animation as a part of this reluctance motor vertical. You can call it different dimensions cross section area of the machines like. And then you can have a typically the axial flux reluctance motor for generator application, like a structure of the generator and as a part of the wind turbine structure of this reluctance motor. Then typically in robotics and automation, how this reluctance motor look like with the power winding and so on. Right side you can have a look at photograph of this typically axial flux reluctance machine. And then typically aerospace and aerospace system, how this reluctance typically the motors look like, and what is the typically the winding shape, what is the typically the different parts of this. Like they are very much preferred in aerospace industries because they don't have magnet and they don't have any part typically on the rotor, so they are suitable for even operation at typically at high temperatures also, or in home appliances either for vacuum cleaner or maybe for feed mixer grinders or pump, or typically taking example of your water pumping system. So you can have a look of stator component for electric water pumps. Now coming to classification of axial flux reluctance motor. So according to the number of air gaps in the axis direction, the classification can be divided into single-sided, double-sided, and multi-stage axial flux reluctance motor. So reluctance motor will be divided first into two different parts. First is radial flux machine, then axial flux reluctance motor, and then transversal flux method. And axial flux further we divide into single-sided, double-sided, and multi-stage. And then double-sided again we put external rotor or internal rotor. So this single-sided axial flux reluctance motor are more conventional, and motors for single-sided configuration benefit for higher diameter to length ratio. And single-sided axial flux reluctance motor require more mechanical rigidity, notably on the bearings to handle the traction force and keep the air gap constant. And single-sided axial flux machines also have lower torque production capability. However, double-sided axial flux reluctance motor are more popular due to their relatively simple structure as well as the balanced axial forces. And double-sided sandwich structure is now the mainstream configuration of axial flux reluctance motor, where it can provide a simple structure and balanced attraction forces in the axial flux in axial direction. And double-sided structure could be configured either with an external double rotor or internal single rotor. Now coming to classification of axial based on winding configuration, we can have a conventional winding or we can have a toroidal winding. And typically you can have how look like a typically the flux path into, looking conventional a wound axial field machine, how the winding is really put it, and then how is the flux path into that, like, and how the toroidal wound axial field typically typical reluctance motor and flux path into it. So you can have a look of flux path in the both the machines. Like, now coming to operating principle of axial flux reluctance motors. The axial flux will follow the minimum reluctance principle, and when the stator coils are excited, the flux generated has the tendency to move the rotor from a position to the larger magnetic reluctance to the position with the minimum reluctance. And with the one stator and two rotors, a three-phase 6x4 6 stator and 4 rotor poles machine having a sandwich structure, the stator is in the middle of the two rotors is considered for operation for axial field reluctance motor. So you can just have a look of it. Typically a typical three-phase 6x4 axial flux motor, and each stator pole has two parts. First part is surrounded by the coil, and the second part acts like a back iron and provides a path for the magnetic flux. So you can just see here how stator part 1 and stator part 2 look like, and how the rotor as well as typically the coils look like. So then you can have a probably the flux distribution with the finite element, and how the single stator and rotor pole pair, and how the simplified sectionalized cutting weave in by jet plane, typically with the flux line. And then how the relative position of stator pole and rotor pole changes of the phase inductance. This phase inductance variation is similar to conventional one. Typically under lying position as well as during ideal phase excitation profile during the rising inductance or falling inductance. Like, now coming to typically the design equation of axial flux reluctance machine. So the output power equation represents the relationship between the output power and various geometric and control variable of the motor, such as inner and outer diameter, stack length, pole height, pole arc angle, and number of turns. The output power can be derived from the input power as P out equal to Ke into Kd, VDC, and I into M, where K is the efficiency ratio, VDC is the input DC voltage, and I is the phase current, and M is the number of simultaneously active phases or excited phases in a particular instant of time. Now the duty cycle ratio Kd is defined as Kd equal to theta C and C Nr upon 2 pi into Ns by 2, where theta is the conduction angle in mechanical degree, Ns and Nr the stator and rotor pole numbers respectively. And VDC can be expressed as VDC equal to Rs into I plus d lambda upon dt, which can be, because Rsi is a quite small compared to this, we can approximate d lambda upon dt. Then we can say VDC equal to approximately d lambda upon dt, that is lambda a minus lambda u divided by theta c by omega. So where theta c is the angle when the flux linkage varies from lambda a to lambda u, and lambda a u are the maximum and minimum phase flux linkage, which can also be regarded as the phase flux linkage at a lying and a lying position. And the omega m is the mechanical angular speed, which can be derived as a function of the rotor speed in rpm, that is omega m equal to 2 pi into rpm upon 60. And the stator and rotor poles are usually share the same value for axial flux reluctance motor. Stator pole arc angle beta s is used here to be consistent with the output equation of the conventional your radial field reluctance motor, which usually have a smaller stator pole arc and therefore theta c equal to beta s. Thus the voltage can be recognized as Vd is equal to lambda upon dt equal to lambda a minus lambda u divided by bs upon beta s upon omega m. And at the aligned position for the axial flux reluctance motor considered here, therefore the phase flux linkage can be written as lambda a equal to phi tph equal to b into pi in bracket d to power 4 minus d to power 3 divided by 4 into beta s into tph, where term pi in bracket d 4 square minus d 3 square into tph and im is the area surrounded by the phase coil. And the equation, this equation is similar to the classical power equation of radial flux reluctance motor. And then you can have a cross section of axial flux reluctance motor, how the look like a coils typically, how the all dimensions like d4 the outer diameter, how the beta r beta s all geometries are defined here typically in the diagram of stator as well as of the rotor as well as coil. So compared to the conventional radial flux reluctance motor output equation, the output power equation of this particular axial flux reluctance motor mainly depends on the stator diameter, and unlike the radial flux reluctance motor, this value is independent of the stack length, and the derivation of the power equation focuses more on magnetic loading, as the B is the saturation flux density of the material. So for this axial flux reluctance motor, the slot area for the copper depends not only on the space between D2 and D3, but also on the stator stack length, and from this point of view, the output power also lies on the stack length of the machine. And in order to determine the final machine geometry D1, D2, D3 and D4 as well as the stack length need to be decided. So for this axial flux reluctance motor, equal amount of flux will go through the two parts of the stator core. So therefore, they should have the equal area of volume, that is pi d to power 4 minus d3 square by 4 into beta s equal to pi d2 square minus d1 square by 4 into beta s. So in practice, the distance between d2 and d3 should be limited, otherwise it may lead to poor utilization of the core material, especially for the rotor. Therefore, this distance is usually small compared to other dimensions, and for this initial estimations, it is assumed d2 equal to approximately d3, and hence d2 equal to d3 and equal to under root d2 power 4 plus d1 square by 2 under root of 4. The diameter ratio k d power to d1, which can also be written as k equal to d out upon d in, is one of the most important parameter in the design of an axial flux machine. So recognize the term d to power 4 minus d to power 3, and using the definition of diameter ratio k results in d to power d4 square minus d3 square equal to d4 square minus d4 square plus d1 square by 2 equal to d4 square minus d1 square by 2 and equal to d4 square divided by d1 square minus 1 divided by 2 d to power 4 square divided by d1 square into d4 square equal to k square minus 1 upon 2k square into d4 square. Therefore, power equation can be written in terms of diameter ratio and the core outer diameter as P out equal to K multiply K square minus 1 divided by 2K square into D to power D4 square, like. So where the K is the motor output constant and given as K equal to KE KD pi square by 120 in bracket 1 minus lambda U upon lambda A into beta TPH IN IM, where K this equal to can be approximately KE KD K1 K2 beta B TPH and IM. Total stack length of the motor is the sum of twice the air gap length, stack length, stator stack length, and twice the rotor stack length. Now coming to the challenges in axial flux reluctance motor, the torque ripple reduction in axial flux reluctance motors, the winding configuration for copper loss reduction, and soft magnetic composites for axial flux reluctance motor. The construction and assembly of the axial flux motor involved large number of parts than that a comparable radial flux machine. Unlike the conventional radial flux SRM, there is a much higher axial force, so the bearing selection of axial flux reluctance motor also need special consideration. Now coming to typical example of finite element design of axial flux reluctance machine. So designing a finite element model of axial flux reluctance machine involves several parts such as geometric creation, second mass generation, then third the material property, Fourth is the boundary condition. Fifth is the solver setting. Sixth is the analysis. 7 is the post processing. 8 is optimization. 9 is validation, and 10th is the iterative design. Now coming to the case study 1 as a design of typically of axial flux reluctance motor for electric vehicle. So for this case, first case study, a segmented rotor double-sided axial flux reluctance motor is chosen for detailed analysis. A doubly-sided radial flux reluctance motor is designed and compared with the double-sided axial flux reluctance motor in terms of torque repel, average torque, efficiency, and power density. The results indicate superior performance of the optimized double-sided axial flux reluctance motor, especially in terms of average torque, which is 26% higher than the torque produced by the double-sided radial flux reluctance motor. And here you can just see in the configuration of segmented rotor double-sided axial flux machine, the diagram shows the single-sided and double-sided rotor topology, B double-sided and single-sided rotor, and the C the pancake topology. So now double stator and single rotor topology design equation is as per axial flux SRM VDC minus RPHI equal to d lambda upon phase upon dt, and by neglecting the phase resistance, the phase voltage can be written as VDC equal to lambda phase upon dt equal to LA minus LA saturation minus LU upon T into I, where LA saturation and LU are the saturated underlying phase inductance respectively. T is the period of time when the rotor move from unaligned to aligned position, and given as T equal to beta s upon omega, where omega means the angular velocity and beta is the stator pole through angle, and the variable KL is defined as the ratio of underlying inductance to saturated inductance, as KL equal to LU upon LA saturation. And typically the voltage equation can be written as V equal to LA saturation I omega upon beta s equal to 1 minus KL. And at the aligned position, the flux linkage equation can be written as LA saturation I equal to NPH into 5pH equal to NPH beta pole into A pole, and NPH is the coil turn per phase, and B pole and A pole are the average flux density and area respectively of one stator pole, and the stator pole area can be calculated as A pole equal to beta s by 8 in bracket dO square minus di square equal to beta s dO square upon 8 into 1 minus ks square. So dO and di are the outer and inner diameter respectively of the stator disc, and Kc is the ratio of inner diameter of the outer diameter, and LA saturation I equal to NPH beta pole divided by B pole upon 8 into dO square minus 1 minus Kc square, and the electrical loading and the output power of the double stator axial flux reluctance motor are written as AM equal to 2 NPH I divided by pi bracket dO plus di by 2 and equal to 4 NPHI divided by pi d0 into 1 plus Ks, where PO equal to n eta Kd VDC into I, and where the eta is the efficiency and Kd is the ratio of actual duty cycle of the phase current to its maximum allowable duty cycle, which is calculated as Kd equal to 2 Nr into alpha by 360. Nr is the number of rotor poles, alpha is the actual conduction angle in each stroke. Output power of the double stator single rotor axial flux reluctance motor equal to that PO equal to pi square eta Kd into 1 minus KL upon 960 into beta pole AM into Nm into dO cube into 1 minus KL Kc square into 1 plus Ks. And it should be noted that Nm is the mechanical speed of the rotor in RPM, and the previous equation can be arranged to calculate the outer diameter of the double-sided axial flux reluctance motor, and given as dO equal to cube root of 960 PO divided by pi square in eta Kd into 1 minus KL into B pole AM Nm into 1 minus Ks square into 1 plus Ks. And then calculation of outer diameter requires the value of input parameter, output power, speed, magnetic and electric loading, and initializing the remaining parameters. So using the previously discussed electrical loading, the number of winding turns per phase is calculated as NPH equal to pi d0 into 1 plus Ks into M upon 8I, and the wire diameter is calculated based on the assumed value of current density delta and the stator RMS current IRMS. So dW equal to under root 4 SW upon pi equal to under root 4 IRMS upon pi into delta. So the stator slot area is calculated as slot equal to NPH into SW upon NS upon F, where M, SW and F are the number of phases, wire cross section area and the slot fill factor respectively. By choosing rectangular stator pole, the stator slot opening and the slot height can be determined by the following formula: WSO equal to in bracket 2 pi upon NS minus beta S into DO plus DI divided by 4 and DSH equal to S slot upon WSO. So the conductor length per phase resistance and copper loss can be calculated as L wire equal to NPH in bracket 1.1 into DO minus DI plus pi upon NS into DO plus DI, and RPH equal to L wire RW in bracket 1 plus alpha into theta minus 120 bracket 4, and PCU equal to M RPH theta into I RMS square, where RW, alpha and theta are the conductor resistance per meter at 20 degrees Celsius resistance coefficient and working temperature respectively. So a nonlinear magnetic equivalent circuit is developed to calculate the value of KL, leading to a more accurate analytical design procedure. So MEC is established at aligning and unaligned position of the rotor, since the value of K is solely dependent on these two positions. When the magnetic flux is associated with the aligning and unaligned position are determined, KL is simply calculated as KL equal to psi A unaligned divided by psi A aligned. And typically you can have a nonlinear permeance network of doubly-sided axial flux reluctance motor as a nonlinear permeance highlighted typically in the red, and full load model at aligned position and reduced model at aligned position. Similarly, nonlinear permeance network of this reluctance at, you can call it highlighted in red, with a full model of unaligned position and reduced model of unaligned position. And typically here the parameter dimensions of doubly-sided reluctance motor at the air gap tubes, aligned position and unaligned position. And typically this is the case of nonlinear algorithm of the hybrid design procedure. So we start with input doubly-sided axial flux reluctance motor rating and main parameter, analyze the value of KL and efficiency eta, calculate the doubly side axial flux reluctance motor dimensions and electrical parameters using equation 10 to 20, then develop the permeance network and calculate the linear permeances with a function or iron BH curve and calculate the permeability function mu equal to F H upon H, and initialize the BH and calculate the iron permeability, calculate the iron linear permeances, solve the permeance network and calculate the new value of P and H iron parts, do the initial value and new value of the B and match. If no, you have to go back and then start again this, and if yes, calculate KL, and now you have to check like do the initial value calculator of K, L and eta match. Yes, finish. If no, then you have to again initialize the value of KL and efficiency and go in iterative manner for calculation of this hybrid design. Now the doubly-sided axial flux is designed with the rated power 100 kilowatt at 3000 rpm, and further specifications are listed here. The output power 100 kilowatt, nominal speed 3000 rpm, DC link voltage 440 volt, outer diameter 370 millimeter, inner diameter 140 millimeter, active length 111 millimeter, number of stator pole 18, number of rotor pole 12, axial length per side millimeter in 0.5 millimeter, number of turns per coil 5, stator slot opening 20 millimeter, stator slot depth 28 millimeter, stator yoke length thickness 18 millimeter, and rotor length 18 millimeter, and slot fill factor typically 50%. So you can see here how using finite element the vector plot of the magnetic flux density distribution in a doubly-sided axial flux machine at the rated current, aligned position and typically aligned position. And you can say flux linkage and static torque rotor position of doubly-sided axial flux machine. So red is the torque, how it goes with the rotor position, and how, and is the typically blue is the your flux linkage. And here the flux linkage static torque per position of doubly-sided in different position, typically doubly-sided unaligned position, doubly-sided aligned position, and with the radial field. So you can clearly see the flux here is much higher than the what you have in case of radial field. Like, and typically you can find out the flux linkage and static torque per position of doubly-sided optimized one and non-optimized the black, and typically the radial field. So you can see torque pulsation is also less in case of this radial field, optimized double-sided radial field axial machine. Now typically coming the main parameters for the doubly-sided axial flux motor and the radial field. So you can just see what is typically the optimized and no optimized RPM. Typically here output power 100 kilowatt 99, doubly sided radial flux is 79.5 kilowatt, then copper loss, and typically the efficiency here it is higher 96%, power density is 8.38, and torque ripple is also less 35%. Now coming to case study 2, comparison of the radial flux reluctance motor with the axial flux reluctance motor. So comparison of 8/6 radial field and axial flux reluctance machine. A performance comparison between a radial flux reluctance motor and axial flux featuring equivalent teeth active surfaces. So dimensioning at equivalent active surface from the existing 8/6 radial flux allow us to compare the inductance waveform at the different current level and therefore the torque waveform with the axial flux radial field machine. And here the comparison of ATL and axial field. Typically you can see how the typically looks like with the stator radius of 32 millimeter, then axial stator 2.5, maximum rotor radius 20 point, minimum radius 39, stator teeth 8, rotor teeth 6, turns per phase 520, stator teeth opening angle 19.2, rotor teeth angle 19.975, shaft radius 10.5, and air gap thickness is 0.35 millimeter. And typically now you can say flux path for the double sided stator assembly and for axial flux typically in 3 models. The comparison of 8/6 and radial flux reluctance machine, how typically they look like the 2 cases, and the reluctance motor basic reluctance network for radial flux reluctance model and axial flux reluctance model, and the inductance variation from radial to axial flux. So here you can see you have a higher aligning inductance is higher for axial flux 231 compared to 160, and typically opposition also is a quite lower 13.4 compared to 29.5. I mean, and you can see clearly how the 3D model looks like, and you can just see how as a conclusion higher aligning level. I mean, you just have a axial flux machine is red, so how you have inductance variation much larger in case of axial field compared to radial field, and how the torque is much higher in case of your axial field compared to radial field for 5 ampere for both cases. Now coming to case study 3, comparison of radial field with the axial field reluctance motor. So principal design and analysis of a novel axial flux reluctance machine with full pitch winding structure. So conventional reluctance motor also known as short pitch reluctance motor, since they have a short pitch winding, and full pitch winding produce higher torque compared to the yours you can call it the short pitch with the mutual coupling of between the phases due to their full pitch winding, and the full pitch axial flux reluctance motor is powered by combining axial flux design and full pitch design. And typically you can say 3-phase 6/4 motor for yours you can call it for full pitch winding, and how the your short pitch winding look like the winding structure, and how typically the full pitch winding and your short pitch winding look like for 6/4. And just to give you idea for axial flux machine, and position of rotor and stator pole align and align condition, and then typically inductance change due to position with this. I mean, in the typically the 2 cases for the current like inductance variation, and then you have a single you can say how the inductance typically angle current and torque variation is there for your short pitch and your full pitch winding. And typically you can clearly see full pitch winding certainly have the higher torque, I mean typically compared to the your single your short pitch winding, and typically in terms of equal copper area. And then the typically the variation of self inductance for your short pitch and full pitch. So you can see here the inductance variation is much better in case of full pitch winding. And then typically flux density distribution of single short pitch and full pitch winding, I mean in the 2 cases. And the very comparative magnetohysteric analysis, typically the in case of how the full pitch and single pitch, I mean your torque ripple reduces your full pitch winding, and how the your average torque percentage is the change corresponding to that. So coming to conclusion, the proposed full pitch axial flux model achieve up to 15.7 higher torque density than the basic a short pitch axial flux reluctance motor model at different currents and equal copper losses, and the proposed full pitch axial flux reluctance motor can be considered as an important alternative machine, especially for electric vehicle technology and different technological fields, with the advantage of higher torque density and axial geometrical structure. Now coming to numerical problems. So question 1, which is the following statement regarding axial flux machine true? Axial flux motor have a simple construction compared to radial flux motor. The explanation is axial flux motor often have a simpler construction compared to radial flux motor. This is because they have more straightforward winding arrangement and fewer components, leading to easier manufacturing and your assembly process. Question 2, which of the following characteristic feature of axial flux motor typically package like design? An explanation: axial flux motor typically have a package like or disc shaped design with the rotor and stator allowing for a disc configuration, allowing for a compact and space efficient motor design. Question 3, what type of flux path does an axial flux motor have? In axial flux motor, the magnetic flux path runs parallel to the axis of rotation, hence the name axial flux, and this is in contrast to the radial flux motor where the flux path is radial and moving from the center to periphery of the motor. Question 4 is the what type of winding arrangement is commonly used in axial flux machine? Explanation: the axial flux motor often utilize distributed winding arrangement where the windings are distributed along with the length of the stator teeth, allowing the better utilization of magnetic flux and reducing losses. Question 5, what type of cooling method is commonly used in axial flux motors to dissipate heat? The axial flux motors commonly use air cooling method to dissipate heat generated during the operation, and this may involve natural cooling or force cooling, air cooling for using fans or blowers. And question 6, the air gap in the axial flux motor is typically narrower than the radial flux machine. Explanation: narrower than the radial flux SRM. Axial flux SRM typically have narrow air gap compared to the radial flux, leading to higher magnetic flux density and increased torque density. Question 7, a three-phase single layer double rotor axial flux reluctance motor will be to be designed with the rotor speed of 1000 rpm, and geometry parameter d1, d2, d3, 4 are given in table. Calculate the dimension of ratio of the motor and the output power. So where d1 is 50 mm, d2 is 90 mm, d3 120 mm, d4 150 mm, g is 0.5 mm, and k equal to 50,000. So diameter ratio is k d4 upon d2, that comes putting a value 3, and output power is po equal to k is k square minus 1 divided by 2 k square into d4 square, and putting a value p comes 500 watt. Now question 8, three-phase single stator double rotor axial flux machine is to be designed with a rated speed of 2000 rpm. Geometric parameters g1, d2, d3, 4, and strand rotor pole are beta s and beta r, and the stator pole stack length lr and ls, and air gap g as number of turns are listed, and is suggested to that the motor operates at the knee point b equal to 1.5 Tesla of the magnetization curve, the lying position. At the dimension is d1 equal to 40 mm, d2 70 mm, d3 90 mm, d4 110 mm, beta equal to beta is equal to beta r, that's 30 degree, ls equal to 60 mm, lr equal to 20 mm, and the g equal to 0.5 mm, tph equal to 32, the beta b flux density 1.5 Tesla, A equal to 20,000, I equal to 5 ampere, K equal to 0.5, Kd equal to 1, K1 equal to 0.0823, and K2 equal to 0.7. Now calculate the flux linkage at line position, calculate diameter, ratio K, calculate the motor output coefficient K, find the generator power, calculate the total stack length of the motor and the flux linkage. Solution is the flux linkage given lambda equal to B pi in bracket d4 square minus d3 square by 4 into beta into tph, putting value here beta equal to 1.5 Tesla, d4 110 millimeter, d3 90 millimeter, beta s equal to 30 degree, tph equal to 32. So putting this lambda a comes to be 38.95 milliweber, and the diameter ratio is k equal to d4 upon d1, that is 2.75, and this the motor output constant is k equal to k kd, k1 k2 beta b tph and im. So putting value it comes k equal to 66,360, and the output power given po equal to k minus k square minus 1 divided to k square by d2 d4 square. So putting value it comes typically 348.39 watt, and the total stack length is LST equal to 2 into air gap plus stator length plus 2 times rotor length. So putting a value here, so it comes LSTK comes 71 mm. And these are the some of the references which are referred to develop this material. You can have a look of these, and thank you very much.